So what I'm going to do today is talk about, is it lab 2 or no, I think it's lab 3. Wait a minute. Lab 3. And this exercise 3.14. So I'm going to just launch into talking about this lab here, and basically we'll solve it together. And but before I do that, is there any important issue that I need to bring to address before we move on? This one, I don't think this is going to take the whole period, so we'll have more time after I finish this problem to do some other things. All right, let's go ahead and do that. And what I'll do is I'll do this on a lab machine today, because this is not a graphics program. So I'm going to use PuTTY and log into a lab machine, and then we'll use the console window to solve the problem. We'll see if we can't log in, then we'll solve the problem a different way. Let's see what's going on here. There, we're in. Okay, and let's just go ahead and log into a different machine. So our lab room is JB359, and the machines are numbered from 0 to 30 or whatever. So we'll log into 4, say. We're the only user on that machine right now. Okay, so I've got a folder called CSE201, and let's go ahead and make well, you know what I'm going to do here. I'm going to do ls-a to show all, and I see that I have a .svn folder in there. I think that this is you know what? I'm gonna restart everything. I'm gonna delete everything in here, and so I'm in this folder. So I'm gonna remove recursive force the current folder, the contents of the current folder. Now there's nothing in there, and now I'm gonna check out just to make sure I have an up-to-date copy of everything. I'm going to check out my repository, and let's see, what would that be? I'm going to take a look at that. Let's see. So here's, in lab 1 we have the URL for the repositories. Is this how I have it? Turner Linux, maybe that's it. That's it. And oh, there's an error. Nothing is there. Let's see. Let me try. Let me take a look here. I just want to see if I have anything in there. There's nothing in there. Maybe it's under just Turner. Nothing there either. I think I have Turner Windows in there. Whoops, Windows. Nothing in there either. Maybe it actually produced a .svn folder, so that means I have a repository, but it's currently empty, so we can work from that. So let's go ahead and make a folder. It's P Let's check that. P314. If someone has a book, can you verify that that's the problem with the projectile, the cannonball? It's the cannonball problem. Okay. Now once again, this is a console. This is not a graphics application. But later in the course, we're going to revisit this particular problem, and we'll do a simulation of the cannonball moving. All right, so this is preparation for a visual simulation that we'll do later on. So today what we're going to do is do a do a simulation of a cannonball being shot straight up into the air and then falling back down to the earth. Okay, where is the cannonball's position at each point in time? That's the problem. So it won't be a visual simulation, but it'll be a numerical simulation. Let's see. So we need a main. Let's go ahead and start a new problem. And I'm just going to grab that hello program. Oops, this is not it. Once again, if I was to do a graphics program, then I would grab this alternative hello program code. And for Windows, I would have something slightly different. All right, let's look at that. And on Windows and Visual Studio, it's very useful to do this operation, but at the command line prompt, we don't really need that. So I'm going to take that out. It simplifies the code a little bit. And I'm going to run a utility called screen, so I can have a couple of virtual screens to look at. Screen is not there. I'm going to install screen. Let's see. Oh, I can't install screen. It's not on the system. Okay, I can't use screen. I got to ask Ken Hahn to install it for me, because I don't have administrative privileges on this system. All right, so let's go ahead and build the program and run it. So there's the high. All right. Now, what I want to do is, let me just put it right inside the source code. I'm going to talk about the problem. We're not going to start coding right away. We have to understand what the problem is about. So I'll just put some comment in here. Put it right inside the source code. Let's see. Pretty slow. Look at this. VI is inserting stars for me here. All right, if this is too slow, I'm going to run locally. It's too slow. I don't know what the problem is. The network is slow right now. Let's give it another chance here. So what we're trying to simulate is if we shoot a cannonball straight up in the air, where is its position relative to the ground at time t equals 1, 2, 3, 4, like that? All right, so let's think about that. Has anyone solved the problem? Just wondering. Oh, okay. It's just way too slow. We're going to have to abandon ship. This is not going to work. I'm still waiting for the command to go in. And just get out of here. I'll do it locally here. I'll use Visual Studio. So here it is. Start it up right there. So the book gives the equation that is used for predicting the position of the cannonball at time t. So we're going to take a look at that equation. What we're going to do is we're going to use the equation to predict the location of the cannonball, and then we're going to use an alternative method of computing the position of the cannonball. We're going to compare those two methods. This is running slowly too. So let's see. I'll add a new project. Console application. And it's P, what was that again? 316? 314? Yeah. 314. And just going to use my standard settings here. Okay. Get rid of these. Add a new item. C++ file. Main. And let's grab our hello program from up here. And here it is. We're not going to need user input, but we might do something like this. So let's just go ahead and do a little bit of work here. And that's it. So build. Did that succeed? 5 succeeded, so I'm building every project in the solution. Let's run that. Up. It's not right. Sorry, I gotta just kill that. I'm gonna make this the startup project. Wait a minute. I'm gonna right click on this. Make startup project. Is that in here somewhere? It must be down here. Set as startup project. There we go. Now if I press F5, I get that. Okay. Alright, let's put in some comments here. And I'm going to do it like this. So this is called a multi-line comment. And slash star opens the comment. Slash and star slash closes the comment. Everything in between is just a comment. It's not attempted to be. It's not translated into machine instructions. So let's do a table. So we're gonna have the time and position of the cannonball. Or maybe we'll call it height. Right? Let's call it the height of the cannonball. And this is our. So the time will be in seconds, and the height will be in meters. And what else are we going to do here? Let's start by using the equation. So let's see, at time 0, the cannonball is on the ground. So it's going to have height 0. So at time t 1 second, where's the cannonball going to be? Actually, and in the book they use the variable s because I think they use that in calculus textbooks. Where is the projectile located? It's something that's moving, something that has acceleration. Let its position be represented by s. That's a typical variable. So where's the cannonball at these different seconds? And let's go ahead and let's compute that using the formula. And what's the formula? It looks like this. So the position at time t, so S of t, the position of time t is minus 0.5 times this thing called a gravitational constant times t squared. That's one way. That's a standard way of representing t to the power 2 or t to the power something. And then we add to it v sub 0, and I'll write it like that, times t. So that's the equation that you get in a calculus textbook, or maybe a physics textbook. So we're not going to go into why that is. We're not going to derive that. That's a topic for a different class. We're going to use this. Now G, what is G? G is it 9.8, 9.6, 9.8 meters per second squared. And so that means we can, this is the, here's the formula. If given a time t, say like 0 seconds or 1 second, plug it into the formula, figure out where you are. Where's the cannonball? All right, that's the formula. And well, we're going to talk a little bit about the formula, but this V0, you know what that V0 is? That's the initial velocity, because the cannonball is subject to acceleration because of the gravity. The force of gravity causes the cannonball to accelerate. So that means the velocity, acceleration means the velocity is not constant. The velocity changes, the speed changes. So V0 represents the initial speed, the speed at time t equals 0. So we need that. So we're going to have to pick a value for t0. I'm going to pick 15. So I thought about the problem before coming to class this morning, and that's a convenient number. And so let's see what the equation says. So at time t equals 0, then we basically have this summation here. So we have this term plus some other term, and both terms you're multiplying by t, or t squared. And so if we put 0 in for t, we're going to get 0 plus 0. So which makes sense, right? The cannonball at time 0 is on the ground. It's in the cannon. All right. So this is the value 0. So the height of the ball at time 0 is 0. But what about time 1? What is the height of the cannonball at time 1 second? So t represents seconds. So this will be, and let's do this. Let's simplify this a little bit. Let's suppose we're not on Earth, but we're on a planet that's approximately the same size as Earth. So we're going to take g equals 10 rather than 9.8. So these are our assumptions. It just makes it easier to fill the table in here. So let's take a look at this one. So this would be minus 0.5. Well, actually, if g is 10, then this is half of 10, so it's minus 5. So it would be minus 5 times t squared. Well, t is 1, so that's 1, plus v0, which is 15 meters per second. That's the initial velocity, and times 1. So, the ball is in the cannon, and then there's the explosion, and the ball shoots out, right? So, I don't know that much about physics, but I think the way that engineers and physicists deal with that situation is they say, well, that's an impulse force, that explosion. And actually, the cannonball goes through a process of accelerating. But for practical purposes, we can assume that there's no acceleration, and that we'll just start with some initial velocity. So we start with a velocity of 15 meters per second. So that's the velocity that the ball attains almost instantaneously after that shot, after the explosion that pushes the ball out. So what do we get here? We get 10. So after 1 second, even though the ball started at 50 meters per second coming out of the cannon, after 1 second, it's, I'm sorry, this is a distance, isn't it? So that would be, it's 10 meters in the air at 1 second, 10 meters in the air. So let's do the same thing for t equals 2. And once again, it's minus 5 times t squared. That would be 4. So t is now 2. Plus 15 times 2. So that's minus 20 plus 30. And minus 20 plus 30 is 10. Is that right? I didn't work this out this morning. I just thought 15 was a good number. So actually, the ball has already started coming down. It's gone higher than 10, and it's turned around and started coming back. So the initial velocity was small. That's so I could get it to come back to the ground soon. So let's actually, I'm going to do this to make it a little easier. And so at time t equals 3, I think it's going to be at the ground, right? So this will be 4. This is t squared. So that's 9. And this is t is now 3. So this is minus 45 plus 45. So that's 0. So at 3 seconds, it returns back to the surface. That's not very interesting. That's when, because the initial velocity is small. So we'll just to see. I just did that just to see the calculations. Maybe the estimate's not going to be that good. So this is the height calculated from the formula. Now there's another way that what we're going to do, which is the book suggests, is to do the calculation using small increments in time. And in fact, to calculate the position of a projectile precisely, the formula is intractable. You can't develop the formula. It's too complicated. There's too many factors. There's air friction. There's the gravitational constant is actually dependent on the distance from the center of the Earth, and perhaps there's other, the surface of the ball, its rotational, and there's a lot of factors that influence its position. So if you want a more precise calculation of where the object is, where the projectile is, you need to abandon the formula and use a different procedure, and you use a simulation, and that's what we're going to do right now. We're going to show how to do this using a simulation. All right. So in the simulation, let's see how that's done. I have to think about it. So let's think, how do we do that? Let me just drop this in here. I'll say simulated here. And once again, that's also in meters. So it better be 0 at time 0. So that's fixed. But what about time 1? Let's think about how we. And I'm following the book on this, so you can look at the details in the book as well as listening to me. At time 1, let's see how they're going to do this is the following: that we have an initial we have a velocity, and the ball is going to move by an amount that's equal to the current velocity times the amount of time. So velocity is distance covered per unit of time. So how many meters do we travel per second? So here, this will be, actually, we're going to call that dt. So this is the simulation will be the previous position, which is 0, plus the change in time, dt, which equals 1. Let's see. Actually, I'm going to put the formula up here. Here's the simulation. The simulation will look like this. So at time t, what we do is we take the position at time t minus 1, and we add the velocity at time t minus 1, and I'll write it like that. That's the velocity at time t minus 1 times the change in time. So that'll be, I guess we call it dt, something like that. And maybe that's a little hard to see. So think about it like this. You're in a car, you're driving 60 miles an hour, right? And you drive for 1 hour. So how many miles do you drive? Well, 60 miles per hour. So I drove 1 mile, so that's 60 miles. It's the same thing here. So we have, in our simulation, at time, now we have, in the car, maybe you don't have acceleration. You're just on the freeway. You're going 60 miles an hour. But in this problem, you have acceleration. So the velocity is changing. So over 1 hour, you're not going to have the same velocity. You're going to have different velocities. Well, it's over a few seconds, right? The ball goes up, it comes down. So what you do is you use an estimate for the instantaneous velocity at some point like t, time t. And so in a small amount of time, some dt, some delta t, how much am I going to move in a very small amount of time, like in a millisecond, a thousandth of a second. If I have my velocity and I move for, how far do I go, given my current velocity, how far do I go in 1 millisecond? So we can do that calculation. That means if we use a millisecond as our simulation step, that means to simulate 1 second, we have to run the calculation 1,000 times. So that makes sense. That's what you use a computer for. That's how you do simulation in a computer. You say, I want an accurate simulation, therefore what I'm going to do is I'm going to make the simulation step as small as possible. Like a millisecond or a nanosecond, whatever you need. This is how you do simulation in computers. Remember, at the very first class I showed that simulation where the water was flowing through the town and destroying the town because it was a tidal wave or something like that. Well, the position of the water elements, so maybe what they did is they took the water and they divided it into small, drops, and they had, 1 million drops, something like that. And then they would calculate the position of each of these elements every millisecond, or every tenth of a second. I don't know, whatever the simulation step is, they had to adjust it, and they had to, so to calculate in very small increments, to calculate the position of all these elements, that it just takes a lot of computation. So that simulation may have taken, several days to compute You know, to get a 1 second or a 10-second animation, you have to spend a lot of time going through very short steps of simulation to compute those positions accurately. So that's what we're going to do right now with the cannonball. And this is in fact what they do, because we're stepping here 1 second, so it's going to be rough. It's not going to be right, because we're assuming that using this table anyway, we're going to assume that the velocity is constant over the 1 second, and then we're going to multiply the velocity by the time by 1 second to get the distance moved. So that's a very rough estimation. So we're going to need to reduce the size of the simulation step to get something more precise. So we'll experiment with that. So here the simulated height would be, or on this one anyway, the velocity is 15 at time 0, and the change in time is 1. So that means we have a height of 15. There we go. So now if we're at 15, also this is the simulated. We need something more than just the simulated height. We also need the simulated velocity. Or speed. And this is in meters per second. So what's the simulated velocity? The velocity at time 0 is 15. That's our assumption, an initial condition. What about at time 1 second? Well, the velocity is, let's see, I gotta remember. I haven't done this problem, so I have to figure it out as we go along here. We adjust the velocity, so we start with a velocity of 15, and that means after 1 second, the new velocity is going to be 15 minus the change in velocity over 1 second. Okay. So so we have gravity. We have the force of gravity. So the ball is going to shoot up, start with a constant velocity, and the force of gravity is going to pull it down. See? So the velocity of the cannonball slows up as it goes up, reaches a velocity of 0, a speed of 0, and then gravity will pull it down. So it'll start going slowly at first and then accelerate and hitting some kind of minus of friction and all that. It's going to re-achieve its velocity of 15. But so velocity is not constant. Velocity is changing. But what is constant in that picture? Does anyone know what's constant? What constant can we utilize in this simulation? Any suggestion? Gravity, yeah, or the acceleration due to gravity. The acceleration due to gravity is a constant. Well, not really, right? The acceleration due to gravity depends on how far you are from the center of the Earth. So if you're a ball going up, gravity decreases as you go higher. So once again, as the book points out, to get a more precise simulation, you've got to take into account changing acceleration as well. But for our purposes, we're going to assume, just like the calculus textbook, that the acceleration due to gravity is a constant. And we're using right now 10, which is an estimate, from a more precise estimate is 9.8, right? So that's an estimate as well, right? So what estimate do you want to use? So we're using 10. So what does that mean? The acceleration due to gravity is 10 meters per second squared. Actually, that's hard to understand, right? I can't explain that right now. I have to think about it and study and read up on it a little bit. What does that mean? Meters per second squared, right? I'm not going to get into that. So 10. So the velocity is going to change by 10 units for every second squared. So the velocity here, no, the velocity changes 10 units every second. So that means we have to subtract 10 here. And we get 5. So our initial velocity was 15, but we're decreasing by an amount of 10 units per second. So now we're at 5 meters per second. All right, let's go back to the simulation step. So actually, in the simulation formula, we have to keep track of our velocity as well as the distance. So the first thing we do is we calculate the new distance, the new height from the ground, and then we recalculate the velocity, the estimate for the current velocity. So that's going to be the velocity at t minus 1. Let's do it like this. This is the velocity at t minus 1. I'm going to make it like this. And, oh, this is not how we did it. This is how we did the calculation, actually. It's the velocity of t minus 1 times the acceleration due to gravity, which is g, times the change in time. No, that's not right. This is plus. So the change in velocity is constant and depends on how much time has elapsed. So g times the change in time, that's the change in velocity. This is the change in velocity. So we take our previous velocity, add our change in velocity, that's our new estimate of velocity. Those are the two steps. So let's take a look now, the simulated height. Let's see, at this point in time, I'm going to check this again. This estimate of 15, or height of 15 at time t equals 1, that would come from this formula here. So I'm going to just double check that. That's s of 0 plus v of 0. Okay, this is for the case. I'm just checking this value right here. So this is, sorry, this is not, I did this wrong again, didn't I? Okay, sorry about that. All right, that's the reason I'm doing the check, just to get that right. So the height at time t equals 0 is the height at the previous time t equals 0. Oh, sorry, the height at sorry. This is what we're calculating. The height at t equals 1, that's the row I'm checking right here. The height at t equals 1 is the height at t equals 1 is the previous height at time 0 plus the velocity, the previous velocity at time 0 times the change in time, which is 1, which is 0 plus 15 times 1, which is 15. So I got that here. I know it's confusing. And then the velocity, now we have to update our estimate of the velocity. So the velocity at 1 is the velocity at 0 plus g, which is 10, times the change in time, which is 1 second. And that's going to be the velocity at 0, which is 15, plus 10, which is 25. Did I do that right? No, this has got to be negative. So this should be negative here. This formula should be negative. Or G is negative, isn't it? That's how they express G. All right, so that's all right. So this is going to be 5. So that's our second row. And then let's keep going. What about time t equals 2? Let's go through the process again. I'll do it like this. I think I got the formulas figured out now. Let's do time t equals 2. Well, that means the position at time 2 seconds is the position at time 1 second plus the velocity at 1 second times the change in time, which is 1 second. The position at 1 second, we can find it from the table, is a 15. And the velocity is, what's the velocity at 1 second? The simulated velocity is 5 times 1. So we're going to get 20. Let me check that. So let's see, the height at 1 is 15 rather. And then the velocity at 1 is 5 times the change in time. So we're getting 20 there. And let's compute the new velocity, the simulated velocity. The velocity at time 2 is the velocity at time 1 plus the gravitational constant minus 10 times 1. So we're going to get, well, v of 1 is 5. So it's 5 minus 10. So it's minus 5. All right, let's do another step. Get rid of that one. All right, let's calculate the height at time t equals 3. That's the height at time t equals 2 plus the velocity at t equals 2 times the change in time, which is 1 second. So our estimate for the height at time 2 is 20 plus the velocity at time 2, which is minus 5. So we get 15 rather. And then for the velocity at time t equals 3 is the previous velocity 2 plus minus 10 times 1 second. I'll just take off the 1 second, use a minus 10, and what's the velocity estimate at time t equals 2? That's minus 5. It's minus 5 minus 10, so that'll be minus 15. So, you know, our simulation is a little out of sync with the formula. Let's keep going here. So at time t equals 4, the formula-based calculation says, well, the ball's been sitting there for a second already on ground. But for our simulated cannonball, it's still coming down. In fact, let's go ahead and do the last step. Should reach 0, I think. I haven't done this, but I think it's going to be 0. So this will be 4. This is 3. And 3. So let's see, this is times 1. That's the same. The height at times 3 is 15. And then plus the velocity times dt, and the velocity is actually the velocity is minus 15. So in fact we get 0 there. So the height is 0. And this, what is the velocity of the cannonball as it hits the ground? I don't know if that's interesting, but let's plug it in there. V equals 4. So that's the previous velocity. That's minus 15 plus, well, this is a constant. It's always minus 10 times dt, so it's always minus 10. So we're going to get minus 25. So we say that the ball is coming down at a rate of 25 meters per second when it hits the ground. So as you can see, the simulation is differs from the formula somewhat. But as we decrease the step size in the simulation, you'll see that the two numbers are going to come into agreement. And let's go ahead and do that. Now comes, so this is the preparation. This is the working out the problem in our heads, right? I'm trying to understand the problem and coming up with an approach. Now this is the kind of problem that you'll think about in physics or in calculus, but now that's where it ends, right? This is the end. That's your lab. That's your physics lab or something like that. But now here we're going to implement it. We're going to implement the simulation. So we're going to code it up. That's the problem. How do we code up this simulation? All right. So we're going to need, we'll have different kinds of variables. So we can start by, I mean, there's a lot of different approaches to doing this. But over time, as you do this sort of thing, you're going to develop a process to translate a problem like this into a running code. And I'd say my hunch right now, the next thing to, unless there's some suggestions, anyone want to comment at this point on how we proceed? Is this the hard part? I know I gave kind of a messy presentation because I didn't actually go through all those details before. I came in late last night. I've been away on a conference and I actually didn't have a lot of time to prepare for this. But so I may have confused you a little bit about the simulation and how to do that. Is there any questions about that? Do you want to talk about that? Or if you don't understand it now, you can think about it on your own as well. Any discussion that you want to have about that? No? Okay. So let's code it up. Let's see what it looks like. And I'm going to start by declaring some variables that we're going to need. So let's, one thing we're going to need is our step size. We're going to call it dt, the change in time. So let's start with 1 second. And what else do we need? We need to know the height. Well, the height will change over time, right? So we're not going to store, like in our table, we're storing, in our calculations, we have a function, the height function. And the table basically shows us us storing the value of the height at these different simulation steps. We could do that. We can store our computed heights at each time and you need something like an array or a vector, but we haven't covered that yet, and we don't actually need it. So when we see height here, this variable represents wherever we are in time. So actually we need that too. Let's have our current time value. And we'll start, we initialize time to 0. So we're at time 0, our height is 0. What's that?
Does that have to be a decimal?
Yeah, well it should be, because dt, what we're gonna do is we're gonna drop dt down to small numbers. We're gonna watch how the simulation converges to what the formula shows us. So we're gonna need to have floating point numbers here. So there's no real integers in this problem except for the iterations, as we'll see. So we've got height and we've got velocity. Remember, we need that for the simulation. And we have acceleration. The acceleration is minus 10. Oh, this is the initial velocity. We're assuming 15, right? That's how we did it. So these are the numbers. So there's an easy first step that you can do. You know, when you go to solve a problem, you've got, well, I got to do all these values. They have to come together. The formulas, I'm going to plug them into. Well, you know, that fuzzy notion as you're getting started in the problem, that's good enough to start doing some coding right off the bat. Hey, let's declare those values. Let's assign to them the correct initial values. Right? You know, maybe we don't know exactly what we're going to do, but we know what we're going to do next. That's the idea. We might not see the entire thing all mapped out in detail in our minds, but we can take the next step. So that's what I recommend you do. I mean, that's what I do anyway. I search for what I feel is clearly the next step in solving a problem. Yeah, question?
Why are you setting velocity to 15 if it's going to be an input?
Say it again?
Why are you setting velocity to 15? Because aren't you going to ask?
No, that's the initial velocity. Oh, you mean ask the user?
Yeah, are we?
No, yeah, it's not bother. You know, we can do that later. But that's the user input, you know, that's another part of the problem. Let's leave that aside. Let's just put, you know, we're solving a specific simulation where the initial velocity is 15. If we want to run a different simulation, we'll just go in there and change the number. Let's not spend time adding features to our program that are not, you know, part of the core issue, which is to figure out how to do this simulation. We can always add that on later on. That's like icing on the cake. Let's bake the cake first.
Okay, I was just trying to make sure I understood the question.
Yeah, that's good. That's a good question.
The problem is to ask that, right?
Oh, are we? I don't know. Does the book say ask?
It says to ask the initial velocity.
Okay. But once again, I would do exactly like this. Let's not, you know, I bet that is one approach. You could actually have the user input those initial states. But we could do that. Sure, we can do that now. Let's go ahead and do that. I'll take that suggestion. So what is the initial velocity? Let's go ahead and do that. I think that's a good idea. If that's how you're thinking through the problem. So there's many different ways of working through the sequence of steps that solves the problem, right? So this is one way to do it. What is the initial velocity? So we'll do Cin velocity. I'm just going to put a new line right in there. let's run it. What's the initial velocity? 15. Okay, there we go. All right, and then so is that it? That's all they want?
Yeah, don't you have to change, give it two variable names? Because velocity, like the
No, no.
velocity-
This is called a definition. We're defining velocity. We're giving it an initial value, and so this doesn't actually matter, right?
What she's saying is you're going to end up changing velocity with your equation.
Yeah,
So
don't
you
you have
have-
to set it to like V naught, like velocity equals V naught and V and V naught?
No, I don't think we don't, because we don't need to save the initial velocity. Yeah, we can do it let's do it that way. Let's go call it let's call it initial velocity. And then we'll have another velocity here, which is our current velocity, like that. That's the idea? And then once we read in the initial velocity, then we'll take our and then we set our current estimate of the velocity to the initial velocity. Was that your suggestion?
Yeah, kind of. I was just gonna, I set my velocity at the top of the double velocity equals V naught, and then I put C in V naught, V0.
You did it at the top?
Yeah, I just set it equal to it.
Okay.
I did. But I guess that's,
But you need another variable called velocity or something, right?
yeah, I have two variables.
Okay, good. And you just named them differently than mine, right? So your names are fine.
Yeah, I did it.
And the order is a little different. There is a million ways to do this, yeah. So that's right. There's many ways to do this. Okay.
You don't have to set your initial velocity, or it says double initial velocity, you don't have to put it equal to 0, it doesn't matter because we're going to input into that.
Yeah. Yeah, but that's a very good question, actually. At this point in time, here, I'm going to put a breakpoint there. If I break there and look at the value of initial velocity and the value of velocity, what am I going to see? According to the C++ specification, it's a random value. If I examine what's in time and height, well, I'm going to see zeros and 0 and 0 because I've initialized those variables. But in this step, I did not initialize these variables. I'm going to break here. So this dt, if I hover over dt, I see, oh, dt is 1 because we initialized it. Time is 0, we initialized it. And height is 0 because we initialized it. But what is velocity? What is initial velocity? I don't know. We didn't initialize it. In other languages, typically there's a default initial state. If you declare a double, it'll be set to 0 by default. That's C#, Java, all the scripting languages. So usually a language will initialize a variable for you that you declare or define. But in C++, that doesn't happen. In C, it doesn't happen. And, of course, in assembly language as well. So whatever happens to be in memory at the time, let's look at it. Look what's an initial velocity. That's a crazy number. That's just, the code is running right now. We're hovering over initial velocity. We're looking at its state. Look at it, -9 times 10 to the power 61. It's just some garbage that's in memory. We didn't tell the compiler to initialize the memory allocated for that variable. We didn't say set it to 0 or set it to -1 or whatever. So it's garbage. And the same with, these are the same, aren't they? I'll bet it initialized them to some funny number for us. Well, it's an uninitialized variable. So what a lot of people do is they like to set these things to known values. So now if we run, we don't have that problem. Now initial velocity and velocity are 0. See, this one is, it looks like the compiler is actually setting uninitialized variables to something to help with debugging, I believe. But we have not yet executed. See, we didn't execute this step yet, so the assignment of -10 to the acceleration hasn't occurred. So if I step forward, watch this. I'm going to go to debug, step over. I mean, just do one step of execution. Now if I hover over acceleration, oh, now it's -10 because I've just executed that statement. Now we're pausing here where this yellow arrow is. Now we're pausing there. So this is a process called debugging. We're using what's called the debugger. We can step through the code and examine the state of the variables. All right, we're running out of time here, so let's move. There's actually a bigger problem. We'll have to continue it inside lab. So one of the things that that this problem relies on is the use of a loop. So the simulation will be, we're going to solve it using a loop. We'll do something like this. Let's do, how are we going to do that? Let's see, we're going to, we're going to basically repeat the following, something like this, repeat the following. And, compute or estimate, compute the next height. Compute the next velocity. So we're going to repeat this. Repeat the following until the ball returns to, repeat the following until 5 seconds. Let's do it like that. So repeat the following while time is less than 5 seconds. So that loop is going to look like this. We'll use a while loop. So while the time is less than 5, we're going to do something. Huh?
Because it says to compute it till the cannon starts to fall back down to Earth. So couldn't you do it?
You can use a different condition for the loop. So I'm saying just finish, let's just go 5 seconds. Well, we can use a different condition. We could use a condition, let's run the simulation until the ball reaches back to the Earth, right? But I chose this condition because it's a little simpler to express, because that condition is a little messy. So as we go along, remember, once again, we're in one shot. It's not like we're getting a hole-in-one at golf here. We're just trying to get close to the end solution. So I chose a simple condition for the loop that we can later replace with something that the book is asking for, perhaps. So if the ball reaches the ground at time 3 seconds, we're going to just get a bunch of zeros after that, right? Assuming that that's what happens here. Are you satisfied with that, or do you want to?
I'm sorry. No, I already did this program.
You did? Oh, that's great.
That's right.
So what is the I mean, because it's going to be messy, actually, by using time. This isn't going to be that. Let me just go forward. Keep those comments coming. Those. Let's compute the next height. So what's the height? The height is going to be this. The height is the height plus the height is the old height plus the velocity times the change in time. And I did that wrong, right? And compute the next velocity. Well, it's the old velocity plus the change in velocity, which is the acceleration times the change in time. That's it. And then let's print them out. Let's print the new height. Let's print the new velocity. And actually, let's print the time. Yeah, that wasn't too bad. $15. Whoa. Something's wrong. What did I do wrong? Time. Oh, the time. Time stays at 0. Time is constantly 0. So we need to increment the time. So that's our time step, right? So we have dt. So time is time plus dt, or change in time. And say 15. That was it? What happened? Time equals time. Oh, plus dt. That's right. What happened? I missed it. So when we get to here, 15, why did it just crash or terminate? While time is less than 5, time is 0. Here we add, dt is 1 second, right? So here is what happened. Does anyone know what happened? Let's do it. Instead of thinking, let's just look, right? So I set a breakpoint, and we're here. Okay, I see the yellow arrow, and the time is 0. And I'm going to step, and the height is currently 0. The velocity is 15, and dt is 1. So now the new height is 15. Current velocity is 15. And now the velocity is 5. So that's correct. And then we output this. Right, so we should see that there. 0, 15, 5. So time 0. Velocity is 15, and the height is 15, the velocity is 5. And then we increment time. So the new time is now 1. We come to here, calculate the height, it's now 20, new velocity. We just outputted this. That's the next one. That looks right.
Should you increment time before your equation? Or before you output?
Well, the thing is, we don't use time anywhere in here.
Yeah, but
So the order doesn't matter.
your output says that at 0 seconds you're at 5
Yeah, you're right. That's right. So we should actually increase the time first. That's correct. Otherwise, the output doesn't make any sense. Oh, you know what it is? It has to do with the see and get. Now, this is the problem. This is a very confusing issue here. And I'm going to show you how I fixed it with this is flush. This is flush the input buffer. And this is tough. You know, I'll show you that it works, and I'll explain this if I can. I don't have enough time, though. So 15, there it is. Because that's hard to read, isn't it? So basically, when the user types in here, when we input velocity, we're grabbing a number from the input buffer, but we leave the new line character in the input buffer, so that when we do the see and get, we read that new line, which the user already entered, and then we terminate the program. So we had to have two see and gets there. I don't want to get into too much, but you need to think about that if you're in fact using this approach. And that's, you know, these input operators, the input streams in C++ are not very user friendly. I have to admit, and that's one of the problems with C++ actually. So you know, it's hard to read this, so I'm going to put in some blanks here. Let's put this in here. Let's go ahead and do that. Does this actually agree with our table? Is this, you know, the reasoning that we did and our estimate here? Did we get it? Do we have agreement there? Oh, first of all, we start at time 1, so we're missing the first row. So 15, 5, 20 minus 5, 15 minus 15, and 0 minus 25, right? Then at 5 seconds, that's too far. So we got that. We did the right. We're matching there. Now, there's a couple of things we need to do here. One is we want to decrease this time step. Let's see what happens if we decrease the time step. And it's hard to read the table, so we'll need to clean that up. But let's look at, based on the formula here, at time t equals 2, the height is 10. And at time t equals 2, the height should be 10. Is that what are we close there now? T equals 2, like the height is 11. See, that's a little better, isn't it? Oh, let's decrease the time step another. Let's go for it here. Let's see if we get even closer to the formula. I'm going to set the time step really small. Oh, it's going to be hard to see things. We won't be able to. Wait a minute. I got to kill that. I didn't really shut it down very well. Let's do. I don't want to get too much on the screen. Time t equals 2. Look at that, 10.1. Look, see, we're getting closer to what the formula gives us. Let's go for it here. Let's not stop now. Let's see how close we can get. Go a tenth at a time. Now it's taking a little longer to run. Let's see, at time equals 2 seconds. It's now we've got to go up quite a bit here. 10.01. We're getting there. I mean, you could just keep going, right? So this is while time is less than or equal to. I'm going to do that. And let's go for it here. $15. So as you can see, you know, now we're converging to what the formula would say. Now remember, see, our simulation is getting more and more precise. And remember, and more precise in the sense that it's converging to what the formula gives us. But remember, the formula is an estimate. And when organizations like the Navy or the Army do calculations on ballistics, you know, they're not using the formula. They're using a simulation. Or NASA, you know, for rockets going through space and going through the atmosphere. There's so many factors that they need to take into account. There is no simple formula or even complex formula that's easy to derive that takes into account all of those factors. So they resort to a simulation. There it is, 10.001. As you can see, we're converging to what the formula gives us. Now, what we'll do in a future problem is to actually, you know, look at the vol visually. So we'll take what we did in this lab and turn it into a visual simulation. And so this is a problem that you should complete in lab. And I'll go over this in lab if you need to. So this is not something I want you to really struggle with, but just but be able to complete on your own. Okay, that's it. We're running out of time, and I'll see those in lab who will come to lab.
Question.
Yeah.
If we're supposed to print out just by the second,
What?
the output just each second, because that's what the problem calls.
Yeah, that's right. So that's what you should do. I mean, we didn't have time to do everything, so they ran out of time, so couldn't do everything.